Hello everybody. So today we are going to have our last video, our last lecture. We will finish chapter 10. So let's maybe start by remembering what we saw in the last lecture. So our topic in this chapter 10 is bandpass noise. So remember that the bandpass noise model that we are considering is obtained by taking white noise, which has flat spectrum, and filtering white noise through an arbitrary bandpass filter. So what we tried to do so far was to study the properties of our bandpass or narrowband noise signal in terms of its pre-envelope and its low-pass equivalent. So here are some of the basic definitions we saw in the last lecture, so let's briefly remember. So the pre-envelope signal is defined by taking our bandpass noise plus J, the Hilbert transform of noise, and we call this as n plus C. Then we took n plus t and then we shifted the spectrum so that we obtained the low-pass equivalent. So some of the main questions we tried to answer in the last lecture were the following. So we know that the bandpass noise signal is white sense stationary because it's obtained by taking white noise, which is zero mean and white sense stationary. So it's obtained by passing it through a filter, so n of t will also be zero mean and white sense stationary. So what we studied in the last lecture was whether all these signals derived from n had also the same properties as well. So we first showed that the Hilbert transform of n was zero mean and white sense stationary. Then we used this to show that n plus t, the pre-envelope signal, was also zero mean and white sense stationary. Finally, we showed that the low-pass equivalent n LPT also had these two properties. So each time the approach was, although a little bit long and mechanical, but simple in principle. So each time we obtained the autocorrelation functions of these signals, and then we looked at the Fourier transform of the autocorrelation functions, and then that gave us the power spectral density. And then each time we saw that the autocorrelation function was a function of tau, it confirmed white sense stationarity. So speaking of the power spectral densities of all of these signals, so I guess by the time we came here, well, at this point, we had write all these results. So this is just a slide from our last lecture, just to remember what we had. So we had a bandpass noise model, noise process, n of t, which has this power spectral density. And remember that, again, to study the spectrum of stochastic signals, we use the power spectral density. So if the power spectral density is bandpass, then we say that random signal has bandpass spectrum. So this was the PSD of the original bandpass signal. So this was the power spectral density of the pre-envelope. Just notice that we only take the positive part, and then it gets an amplification factor by 4 because this power, unlike the case where we had deterministic signals, some g of f here, g plus f would be 2. So the amplitude would have been multiplied by 2 if these were deterministic signals. But since these are random processes, when we look at their spectrum, we look at power. So the amplification factor of 2 in the deterministic case becomes an amplification factor of 4 here. And then the passage from the low-pass, the pre-envelope to the low-pass equivalent was also quite similar to the deterministic case. The action it has is to take the spectrum and then shift it to smaller frequencies. So this was the spectrum of NLP of t. So as we expected, it is indeed low pass, right? The original signal is bandpass spectrum, but its low pass equivalent, the low pass equivalent process has low pass spectrum. Then the final things we wanted to look at was the in-phase and the quadrature components of this. So this is what we are going to first conclude for today. So let's remember what we did about that in the last lecture. So we started with the canonical representation of n of t. Then first notice that the in-phase component and the quadrature component, again, remember their definition. We know how to derive NLP of t from n. Then if you just obtain this process, you write a serial part and the imaginary part, then you have ni and nq. So it was easy to show that they were zero mean, and then we showed that their autocorrelation functions are both given by this expression. So notice that there's some symmetry in here. So Ni and Nq are different processes. They are not the same process. They have different values at different t instance. But when we look at the autocorrelation function of both of them, they are equal and they have this value. Again, we looked at this equation and we said that this is quite similar to the deterministic counterpart. So our n of t is a bandpass signal. Why? Well, this is the Fourier transform of n of t, right? This shape is the Fourier transform of this. Our n hat of t has the same power spectral density. And so something bandpass, you're multiplying them with some high frequency cosine of sine functions, and then you get the autocorrelation functions. So these equations confirm that Ni and Nt are also White-Sands stationary, but the only thing we left unresolved in the last lecture was to confirm that these two signals are indeed low pass. So what we will do today is we will just complete this picture. So we will also add here what the spectrum of Ni looks like. So we will add Sni of f here and Snq of f here. And our natural expectation is that they should look like something like this. So we expect these to have low pass spectrum. Why? Because they inherently come from the low pass process NLP. So these are the real and imaginary components of NLP of t, and NLP is low pass. So we also expect these to have a spectrum that's concentrated at low frequencies. So this is what we are going to first confirm for today. So so we'll do the same thing for the cross power. Here you have the cross correlation functions. We'll also find the cross spectrum of Ni and Nq. All right, so here is the fact. It's summarized in this fact. So what this tells us is when you look at the Fourier transform of Rni here, which is also the same as the Fourier transform of Rnq, so the power spectral densities of the processes NIT and NQT, they are given by this expression. So there is the power spectra of Ni and Nq, and also if you look at the cross power spectral density of Ni and Nq, you get this expression. So, alright, so this part is also going to be a little bit mathematical. We will do the derivations, but let's go through it step by step, and then at the end we will confirm that these are indeed low pass signals. Okay, well, the spectra are concentrated at low frequencies, let's say it this way. Alright, so the proof is quite simple, but it takes a bit of time. So let's begin with the expressions of Rni. So I'll just do it for Rni. Rnq is the same, it's basically exactly the same equations hold. So let's just copy this equation and then let's take its Fourier transform. So let's first remember Rni of tau is given by this expression. So Rn of tau, I'm just copying the previous equation on the slide. So cosine 2 pi fr tau plus the Hilbert transform of this time function, Rn Hilbert transform of tau, sine 2 pi phi tau. Okay, now from now on there is nothing random in this equation, right? It's a deterministic time function, and so on. So let's first remember that let's first write down the Fourier transform of the Hilbert transform of Rn. So its Fourier transform is minus j signum f times the spectrum of Rn of tau, so Snf. Why? Because the Hilbert transform is a linear and it's an LTI operator, and this is its frequency response. So then using this, now we can take the Fourier transform of the whole expression, so we get Sni of f is equal to the Fourier transform of this. So let's take the Fourier transforms. So here, let's focus on this first term. Here you have a signal that's modulated by this cosine. Again, we can look at them, they are deterministic signals. So modulation by a cosine, we know that the effect that it has on the spectrum is to take the spectrum, shift it to the right, shifted to the left, and it comes with a factor of 1 over 2. So let's write this down. So it's 1 over 2 times the spectrum of this shifted to the right, but the spectrum is nothing but Sn. So Sn of f shifted to the right will be f minus fr, plus, again, Sn of f shifted to the left by the cosine, Sn of f plus fr. And then when it comes to the second term, here you have almost the same thing, but instead of a cosine, you have a sine. And multiplication with a sine also has the same effect. It shifts the spectrum to the right and to the left, but with different signs. So instead of the 1 over 2, we have 1 over 2j coming from the Fourier transform of the sine. And then this time we're taking the spectrum of this signal, so this expression, we're shifting to the right and to the left. So when we shift this to the right, that means that we're plugging in f minus fr instead of f. So we have minus j signum f minus fr times Sn of f minus fr. And then we do the same thing this time, looking at it at f plus fr. So the minus sign, the first minus sign comes from the sign, because the two parts have different signs. And then we just repeat the same expression. So we have minus j signum f plus fr, and then Sn of f plus fr. All right. Now we can make a few simplifications here. First of all, minus sign with the minus sign here, they cancel each other. So minus times minus is plus. Then we can just get rid of all these j terms. The j here cancels this one and this one, which makes the equation simpler now. So if we gather all the terms together this time, so we have one Sn of f minus fr factor, which also repeats here. So let's write it. So we were looking for Sni of f. So this is equal to, sorry. So let's see here. So I will just copy 1 over to S minus fr first. And then let's see what we can write next. So one factor comes from here, and then we have a factor of minus signum f minus fr coming from here, right? So 1 minus signum f minus fr. I will leave some space here, and let's write the next term, the Sn f plus fr term. So again, start with 1 over to Sn f plus fr. And then here we have a 1 factor, and then here we have a signum f plus fr factor. All right, you have all these expressions. Now, we know that whenever we see 1 plus signum something, it usually gets simplified. It becomes a unit step function, but let's just write it the correct way. Okay, let's first begin with that one. So 1 plus signum f plus fr. The way I like doing this is I always try to draw. So I draw what a signum is, and I add this offset, and then I look at what it looks like. So signum f plus fr will be this one, right? So it comes, signum f would have the transition at 0, but this one is shifted to the left, so the transition is at minus fr. So this is minus 1, this is 1. So and you're adding 1 to it, then it becomes this unit step function. So it comes at 0 until here, and then it jumps to 2 when it gets the 2 offset. But then we know what this function is. This is a unit step function with a factor of 2, but shifted to the left. So this is going to be 2 unit step f plus fr, right? Now we are doing the same thing for this one. So signum f minus fr means that you have a signum that has a transition at plus fr. So this function, this is fr, this is minus 1, this is 1. So you're subtracting this from 1. So when you do that here, so 1 minus minus 1, you get 2. And then at this point, you have 1 minus 1, so it drops to 0. Okay, so again, this is a unit step function. So in fact, if you compare this, I always get confused writing this. Is it u of f plus f, or is it u of minus f, or where should I put the minus sign? I know that there's a change of direction, but well, the easy way to do it is if you compare this blue one to the red one we already had in here, you see that this is a time or frequency reverse version, right? It's just a symmetric of this. You take the red curve, you flip around the y-axis, you get this one. It means that you're reversing in f. So you take this expression, whatever it is, whenever you see f, you plug in minus f, then you won't make a mistake. So you see that here, if we just take the same expression, u of twice u of f plus fr, but f becomes minus f, so minus f plus fr. For the reversal in f, let's call it that way. So you get the expression for this one. All right, now again, luckily the 2 factors here will cancel. So the 2 cancels 1 over 2, the 2 cancels 1 over 2. So we are left with the expression Sn of f minus fr times u of minus f plus fr, and similarly for the other part. Now what we will do in the next is we will here, to take the last step, we have to, I find it easier to draw and then to see what kind of effect these multiplication with these unit steps really have on the spectra. So, okay, what I like to do is to begin with the original spectrum. So, right, let's begin with Sn of f. I'm just plotting an arbitrary bandpass spectrum, so fc, a peak at fc, another peak at minus, oops, well, just ignore it. It can't be negative, you know it, right, guys? Something is happening with my pen these days. I'm sorry. I won't mess it up this time. Okay. The peak here stays positive. Okay, so this is Sn of f, the spectrum of the original, our original random process n of t. Now let's try to see what Sni of f will look like. So let's draw these expressions. So, so in this first one we have Sn of f minus fr, means that you take this spectrum, you shift it to the right, by an amount of fr. But then there is this multiplication with the unit step that we should take care of. Let's first do this peacefully. So let's draw Sn of f minus fr. So it means that I'll just pick the blue color for that. It means that I'm taking this fc and I'm shifting the peak by fr. Well, here, in fact, there's no assumption made about what fr should be in the equations here. But you can, these expressions hold only if fr has been some certain interval. Now, what we will assume from now on is that fr is something close to fc. I mean, it doesn't take I don't know, an eccentric value like 0 or something very high. So let's assume that fr is something comparable to fc, but not necessarily exactly equal to fc. But for the sake of my drawings, I will take it to be slightly smaller than fc. So if you just take this, the peak, and move to the right by amount of fr, I guess it will fall somewhere like in here maybe. So first one will become something like this. So the peak here, which was at minus fc, will move to fr minus fc. And then the second peak, well, these are symmetric, right? It's because of my bad drawing. They have to be symmetric. So, and then the next one will also shift. So I wanted the black color here. Okay, and the peak here we know where it will be. So this FC will be shifted to the right. So it will be shifted to FR plus FC. So the blue one is Sn of F minus FR. And then if we now take the now we will do the same thing for the shift to the I'm sorry, before that, let's also discuss the effect of this unit step function. So this unit step function takes the whole expression and then it keeps it multiplies it, well, the two factor has cancelled, but it keeps it until the frequency FR, but then for the frequency is larger than FR, it sets the spectrum to 0. So let's just pick some FR, I guess it would be somewhere like in here. So it means that for the first part of the spectrum until FR, I'm just drawing the unit step, so it will be capped. So this peak, this left wing will be capped, but then this one will be multiplied by 0. So it means that actually we have gotten rid of this one won't be there anymore. So if you do the same thing for the right one, and you have Sn of F plus Fr, meaning that you take the spectrum and you shift it to the left. Let's draw that. So I'll pick the red color for this. So this one will be shifted to the left by Fr, so it will fall. For my drawing again, I assumed Fr to be smaller than Fc. So guys, my computer is this running slow, so this is why I have trouble. I'm sorry. I think when this online education is finished, my computer will be happy. Alright, so this first one is going to be shifted to here, so to the frequency Fc minus Fr. And the same thing, the second one is going to be shifted to, let's say, somewhere in here, so minus Fc minus Fr. Okay, so we have the whole spectrum now. But then again, let's take care of this multiplication with the unit step. So here, the frequencies until minus Fr are set to 0, and then the spectrum after that is capped. So let's just draw the unit step function here. So let's pick the Fr value in here. I'm sorry, the minus Fr value. So the values until minus Fr are set to 0, and then the values after that, again, because my computer is responding late. This, we shouldn't have this part. And the values after minus Fr are kept. So you have this. Okay, so it means that this left part of the spectrum is also set to 0. It disappears. So what is left in between is only what is between minus Fr and Fr. So these two peaks, the blue peak coming from this one and the red peak coming from that one, they are left. So now again, what we are trying to do here was to get the expression for Sni of F, but we can write this as follows. We can see it that way. Just take everything right here, this one plus this one, and the blue ones, so plus the blue ones. If you take the all four curves here, and if you multiply with this rect function between minus Fr and Fr, then these two will automatically disappear, right? It is equivalent to the multiplication with these u's. So we can write this as follows. So Sni of F is, so let's take everything. So I take the spectrum, shifted to the right, plus shifted to the left, and then it means that I sum up the red curves and the blue curves, and I multiply everything with this rect function, rect of F over 2Fr, because I need a bandwidth of from minus Fr to Fr, so it has the width is 2fr. All right, so this is the expression for Sni of f. If you want to draw it, you can do it. You just have to, well, let's maybe try it with another color. So black one. So it will just come as 0, and then, well, until here, then it will start rising up. Maybe I shouldn't have attempted. And then it will have some peak, and again it will decay to 0. So my drawing is not very precise, but I guess you get the idea. Okay. Okay, something like this. So now let's go back to the second expression. So we won't prove this one, but it's basically the same idea. So Sni NQ of f. Basically, to obtain this equality, what you do is quite mechanical. It's the same thing. You take this expression for the cross-correlation function. So this expression, you just simply take its Fourier transform by following similar steps. So well, this j here shouldn't confuse. It just means that if you can delete it from here, you would just put minus j here. It's a completely imaginary function. Okay, so well, let's maybe first comment on this shape, although we don't do the derivation. It would mean this following. It's exactly the same expression. Compare these two. It is still non-zero between minus fr and fr because of this rect term. But the only difference is that the it's n of f plus fr term get this minus one sign, minus one factor. So basically, you would still have the blue curve in here, which corresponds to Sn of f minus fr. But the red curve, by the way, we didn't note it. Let's write it here. The red one comes from Sn of f plus fr. But the red curve here would get multiplied by minus 1, right? So it would shift the sign. So, and then you sum up this blue curve and then minus the red curve. So this is what you get as the cross spectrum. So what is important to notice here is that in these two expressions for the spectrum, everything is low pass. So Ni of t, which is the real part of this low pass equivalent process that we obtained here. So this process is a low pass process. Why we look at its spectrum as Ni of f, it's this one, it is low pass. As Nq of f is also equal to that one because the autocorrelation functions were the same. So Snq of f also has the spectrum. When you look at the cross spectrum, well, the expression is slightly different, but then if you take the blue curve minus the red curve, they will still be in the low pass part, well, the low frequency part of the spectrum, right? So everything is low pass. So it just confirms our intuition that the expressions that we had in here indeed took a bandpass spectrum, another bandpass spectrum. After these multiplications with the cosines and sines, it gave us a low pass spectrum. Okay. Right. So let's now comment on the mean square values and the average powers of all these processes. So Ni of t and Q of t, the bandpass signals Nt and N hat. What this says is that they all have the same mean square values. And we haven't shown it, but it can be shown that all these signals are ergodic, so their mean square values are equal to their average powers. So they all have the same average powers. This is what the statement tells us. So let's prove this. So let's go with let's find the mean square value of Ni of t. So we would like to find the expected value of Ni square of t. This is what the mean square value means. But then this means that we are looking at the autocorrelation function of Ni at tau equals 0. But then since this forms a Fourier transform pair with this function, it means that we are integrating Sni of f between minus infinity and plus infinity. But Sni of f is non-zero only within the period. Because of this rect term in here, it's non-zero only between minus fr and fr, right? My drawing is really, really bad. Okay, so then I can just write down the integral from minus fr to plus fr. So, and then within this interval is equal to this value. So Sn of f minus fr plus Sn of f plus fr df. Okay, but then let's now stare at this expression and let's comment on what it should be equal to. So it's maybe easier to discuss on the figure. What this expression corresponds to is the following. I take the blue curve plus the red curve and I integrate it. But then integral is linear, so if I took the blue curve and I integrated it, plus I took on the red curve and I integrated it, it will be the same thing. But then the area under the blue curve plus the area under the red curve, what is it equal to? It's equal to the area under the whole power spectral density of NF, right? Why? I mean, this blue part comes from, well, this blue shaded area. Okay, I want to make it right. So this one is obtained by shifting the spectrum to the right. So this one, blue one, should be come from this shape. And in the red one, the red area here, now it's a shade like this. The red area here would be obtained by shifting this right wing to the left. So the blue area plus the red area is obviously the area under the original power spectral density. So this is nothing but is equal to the integral equals the integral of Sn of f over the whole frequency line. So Sn f df. But then this integral is equal to the, again, it forms a Fourier transform pair with Rn, so it's equal to Rn of 0. But then Rn of 0, we know that it is equal to the mean square value of the original band pass process. N squared t. So since these are real, you can just omit the magnitude sign. You could just simply write it as the square of the process because these are all real. Okay, so what this tells us is that Ni of Q, Ni of T has the same mean square value or the average power as the original process. And Ni and Nq, they have the same autocorrelation function, so it means that Nq of T also has this average power. Now, actually, we could make a nice drawing and table to compare all of these things, all of these signals that we have seen before. We cannot compare them in terms of their average powers. So here we have the comment that the rest follows because the PSUs are equal to each other. So here, let's make this drawing that concludes everything. So again, let's start with the power spectral density of the original process. It's a band pass process, so one peak at Fc, another peak at minus Fc, and so I'll just assign the value 1 here, and then I will make an average power table here. So okay, average power, and I just write down the process. So I begin with the process N of T. Let's assign the value P just for reference. Let's call as P the average power of Sn of it. But then this, if we call it P, it means that the whole area under Sn of f has to be P. So it means that half of it, since this is symmetric, again, remember this is an even function because N of T is a real process, half of the power should come from here, P over 2, and the other half should come from here, P over 2. Alright, now let's continue with the other processes we have seen. So I'll just also put the pre-envelope process here just to remind ourselves what the spectrum look like. So remember that if this is 1, it's got the amplification factor of 4, but it's single-sided. It only takes the positive part of the spectrum. It neglects or suppresses the negative part, so this is 4. But then the area here, if the area here is p over 2, the area here would be, what is it, p over 2 plus 4, it would be 2p. So the average power of the process n plus t would be 2p. But if we also put the Hilbert transform of n into this picture, so remember n of t passes through the Hilbert transform, it becomes n hat of t. How do their average powers compare again? Well, the Hilbert transformer has frequency response minus j signum x, so its magnitude is 1. So the power spectra are the same. So n of t and n hat of t have the same, exactly the same power spectral length. So I could simply write this as the spectrum of n hat of t, so s n hat of f. So let's also add it to our picture. So n hat of t would have also the same average power because it has the same PSD. Now, it in fact totally makes sense that the average power of n plus t is twice the average power of n and n hat. If you think about it, this is nothing but n of t plus j n hat of t, right? You're kind of summing up these two processes, so the powers get also summed up in some way, so it makes sense. Just noticing, remember these were orthogonal random variables. It makes sense. Okay, now if we also look at the rest, so let's continue with S and LP of S. So the spectrum of the random process and LP of T, so S and LPF. Remember that this was just this spectrum but shifted to the left to low frequencies. So again, with the same amplification factor of 4, we will see it here. So let's put 0 here, not forget the signs. So here we'll have the same area, obviously, so the average power is going to be 2p. So let's also add it here, so n LP of t will also have the average power 2p. And finally, if we also add to this picture the power spectral density, I'll maybe try to draw it here. So S n I of f, which is also equal to S n q of f. You can arrange your drawings better than I. So they also remember the spectrum of these guys from our picture. So as ni of f was this, the blue one plus the red one. So basically you take the left one, becomes the blue one in here, so let's just plot. It's exactly the copy of the of one part shifted to the left and the other one shifted to the right. So it will become something like this. But the same factors are kept, right? It just, there's no amplification factor. And Sni of f, which is equal to Snq of f, is the sum of these. I'll maybe pick another color for that. Let me pick another one, green, let's say. So this. So here the PSD is the red area that again, my curves aren't consistent with the drawing. Anyway, you'll draw them better. It shouldn't have had a peak. Never mind. But what's important is the what's under the green curve would be the areas under the these two little hills. But then it means that you're summing up p over 2 with p over 2. So let's write here, and I of t has also average power p, and it's also the same as the average power of nq of p. I'll just put a separation here so that you won't get confused. Okay, so the PSD drawings on the left. Now, but doesn't this make sense? Because if you just analyze an LP of T, it's nothing but it's composed of these two processes. This is Ni of T plus J and Q of T, right? This should have been T, by the way. It shouldn't be F. This is T. Okay, so this NLP consists of Ni plus J and Q, so it also kind of makes sense that you add up the power spectral densities. I mean, you can't claim this in a general manner, but here all these processes have these special properties that I think we'll just prove that these are orthogonal and so on, they're uncorrelated. This is just to give you a feeling about this. These two are, this one is composed of these two. In some way, its power also consists of the sum of the powers. The NLP is kind of the equivalent of this, but only with a shifted spectrum, so their average powers are the same. But then NLP has these composing parts, Ni and NQ, which also have the power, not their power gets divided by two. Half of the power of NLP goes to Ni and half of its power goes to NQ. So finally, Ni and NQ, they end up having the same average power as the original process. This is kind of the picture that we might want to remember when comparing all these processes in terms of their spectrum, in terms of their average power, and so on. All right. Now, well, I guess this part is fine. Yeah, now the following comment is about the orthogonality of the random variables Ni and NQ. So, again, remember, we demonstrated one orthogonality relation before. We showed that n of t and its Hilbert transform n hat of t were orthogonal random variables at each t value. Here we have a similar demonstration to make. So fix any t value. So take a sample from the random process Ni and a sample from the random process NQ at the same time instance. What this says is that they're orthogonal random variables. What does the orthogonality mean again for random variables? It means that you look at their product. If they were complex, one will get the conjugate sign, and you look at the expectation of the product. If you have x and y, two random variables, expectation of x times y conjugate would be their inner product. So to show that they're orthogonal, we should show that this inner product, interpreted in the mathematical way, is equal to 0. But then this inner product is nothing but the cross-correlation function evaluated at tau equals 0. And I'm using the relation between the cross-correlation function and the cross-spectral power spectral density. It is the integral of the cross-spectrum between -infinity and +infinity. But then we saw what this cross-spectrum is. It is here, as Ni and Q of f is just this expression between -fr and +fr. So, of course, multiplied with the j factor. So, so the -j factor comes to the other side of the equality as, j comes to the other side of the equality as -j. So you have this integral to take. But then this integral is equal to 0. Again, why is that? So integrating between -fr and fr, this first part minus the second, but these are nothing but the blue curves and the red curves we had in this picture. So back to here, you're integrating the blue curve and minus the integral of the red curve. You're subtracting the areas, but then these areas are the same. Why? Because it comes from the symmetry of the original power spectral density Sn. So remember, n of t is a real process. Normally, if for complex processes, the PSD doesn't have to be symmetric, but when the process is real, the PSD is a real and even function. It's even, so that whatever shape you see here, the shape here is exactly the same. They are symmetric. So if you take the integral of the blue part, and if you take the integral of the red part, and if you subtract this from the blue one, you get 0. So this is the idea. So this is why this integral is going to come as 0. Again, it's written here Sn of f is an even function of f. Here we show the orthogonality ni times nq is equal to 0 at any t value. But then let's also remember that these are zero mean processes, so the expectation of ni is equal to the expectation of nq, which are both 0. So the orthogonality argument becomes the same as the uncorrelatedness argument. Why? Because the cross-correlation function becomes equal to the the cross-covariance function becomes equal to the cross-correlation function when both processes are zero mean. So these random variables are uncorrelated as well. What this really says is take any bandpass process, find the low-pass equivalent, look at the in-phase and quadrature parts. But there's kind of this, the hint of orthogonality even in the name, in-phase and quadrature. What this confirms is that yes, they are orthogonal. They are more than that. They're uncorrelated. You might even maybe ask, are these independent also? Not in general, but then we will look at some special case under the Gaussian assumption. If these processes are Gaussian processes, we will show that the uncorrelatedness property here also implies the independence. So in general, you can't say that they're independent. The best that you can say is that take any t instant, these random the random variables ni, t, and nqt, these are uncorrelated random variables. Now, you might also ask, okay, I fixed t, I have a random variable, I have another one, these are uncorrelated, but can I also claim that these two random processes are uncorrelated? To be able to say that, we should have looked at ni of t plus tau versus nq of t, so at different time instants. So if the uncorrelatedness assumption or the uncorrelatedness property still holds, even if I look at them at different time instants, then I say that the processes are uncorrelated. Here it's only the random variables obtained at the same time instant that are orthogonal and uncorrelated. So the uncorrelatedness of the random processes does not hold in a general manner, but under a certain assumption it can be shown, and it is the assumption that the noise power spectral density is symmetric around the center frequency Fc. Now again, going back to here, Sn, this is not to be confused with the evenness of Sn of f. So whatever bandpass noise process, a real n of t process, its PST is going to be an even function. That is for sure. So the curve here will be the symmetric of the curve here. That's not what we are talking about. What we are talking about is focus only, let's say, on this right part, for example. And is this shape symmetric around the center frequency Fc? In my drawing, these are bad drawings, but I mean, it should look like something like, it should be a symmetric function. It should be symmetric around this axis. For instance, if this is a triangle like this, well, this is not symmetric around Fc, right? If it were a square, like an ideal bandpass process, it would be symmetric and so on. This is the symmetry we're talking about. So if Sn of f has that kind of symmetry, then we can obtain that Ni and Nq are uncorrelated as random processes. How does it work? It's because the let's first notice that the cross power spectrum Sni and Nq vanishes for all f. Why is that again? So going back to the expression of Sni and Q, this tells us that to get the joint, the cross power spectrum, you should take the, I'll call it again the blue one, and you should subtract the red one. And also we have another assumption to make about the reference frequency. If the reference frequency or the representation frequency is chosen as Fc, so you shouldn't take an arbitrary Fr, you should also choose Fr is equal to Fc. Then let's see what's going to happen. So remember the blue curve and the red curve, so I'll just make a new drawing here. So we are trying to draw J, S, N, I, and Q of F. So the blue curve, taking the representation frequency Fr is equal to Fc, well, this peak, Fr minus Fc, will move to 0. So I have this blue curve centered at 0. And then I have this red curve peak at Fc minus Fr also move to 0. If Fr is equal to Fc, then the peak will be at 0. But then with a minus sign in the cross spectrum. So we have this shape. And if we, again, why do we need this symmetry of the spectrum? Remember that this blue curve comes from this part. So if this is completely symmetric, and if the red one is also completely symmetric, these will cancel each other. If it are something like this, triangular, etc., not symmetric, you won't have that cancellation. But if these are symmetric, as in my picture, they're going to cancel each other in this new drawing. So blue curve minus red curve, you're going to get a flat spectrum for the joint power spectrum, as it will be equal to 0. So this is going to be identically equal to 0. Again, let's write down our assumptions, assuming that Fr is equal to Fc. And the second assumption is that the original bandpass process, sorry, tilde is in the wrong place. The original bandpass process Sn of F is symmetrical around Fc. I'm talking about each one of the individual wings. Okay. So if this assumption is met, then what's happening? The joint power, the cross power spectral density is equal to 0. But then this identically being equal to 0 means that its inverse Fourier transform R, N, I, and Q of tau is equal to 0, which means that the random variables N, I of t plus tau and then Q of t for any tau, they're orthogonal to each other. So since both processes are zero mean, they are not only orthogonal, but they're also uncorrelated, which is, in which case we say that the two random processes are uncorrelated random processes. So here you have a summary of all these observations. Next, we look at this example that demonstrates all these properties that we saw. So let's consider a narrow band noise process N of t, whose spectrum looks like this. So it is band pass, and of course it's symmetric around f equals 0. But when you look at each wing in the right and in the left, it's not symmetric. So it's a triangular function. It's not symmetric around the center frequency. So notice in here that the center frequency is Fc is right in the middle of this, in the base of the triangle. So this end point is Fc minus b, and the other end point is Fc plus b, and similarly at the negative side. So this is fine. So what we're asked to find is the power spectral densities of the pre-envelope process N plus t, the low-pass equivalent process and LP of t, and also the spectrum of the in-phase and the quadrature components. So we will do the same thing twice. So I'll actually solve part A, and then I'll leave part B to you, whose answers also provide, so you can just cover it and then work it on your own. So the center frequency of the passband is chosen as the representation frequency, or the reference frequency Fr. Okay, so let's solve the part A first. So we could first begin with the pre-envelope. In any case, the Fr doesn't change anything for this one. Remember that the spectrum of N plus is related to the spectrum of n as 4 Sn of FUF. So we saw this before. I'm really not. I'm clumsy with the writing pad today. Unfortunately for the last lecture. Alright, so let's just plot it. So what this means is very simply we take this PST, we suppress the left part, we take only the right part, and we don't forget the amplification factor of 4, and that's it. So just copy the same shape. So spectrum is between FC minus B, so the midpoint is here, and then FC plus B in here, so you have this triangular shape like this. So this is F, this is 0. Remember the top value, the peak value of the spectrum is called A in the example, so this is going to be 4A. It gets amplified by 4. Okay. So this was simple, and the next part, let's look at the power spectral density of the low-pass equivalent process, so SNLP of F. But then we know how this is related to Sn plus, so this is just obtained by taking the spectrum of N plus and shifting it to the left by an amount of Fr. F plus Fr. Now here, if we choose, since in part A, we are choosing Fr is equal to Fc. We know that, well, this Fc minus B point should be if Fc is equal to Fr, it should be moving to minus B, and this point should be moving to plus B, so that we have this low pass spectrum. So the left point of the triangle moves to minus B, the right point moves to plus B, and the center point moves to 0. So this is the peak value is the same as in the pre-envelope, so 4A. So this is a spectrum of the low pass equivalent. Obviously, it is low pass as we expected. And next, let's look at the spectrum of the insight on the quadrature part. So I'll just write this down once more as Ni of F. We know that Ni and Nq have the same have the same autocorrelation functions and the same power spectral density, so these are equal. And these are equal to, I will this time write it in terms of this partial definition. So if F is between minus Fr and Fr, means that I'm summing up the right part of Sn and the left part of Sn. So if F is between minus Fr and plus Fr, and then 0 otherwise. You can prefer the rect representation, so multiply the sole expression by rect, rect of F over 2Fr, or you could give the partial definition like this. They mean exactly the same thing. So let's plot this. So I'll first make the first drawing by just shifting these right and left parts to around 0. So Sn of F minus Fr, let's see. So this is Sn of F. So if you shift this to the right, then you're obtaining Sn of F minus Fr. So the first triangle, triangle here will move to here. It will just pass through 0. The middle point will be mapped to 0. So we'll have this one. And again, this one we are shifting it to the right as well, but then it gets outside our rectangle, right? It gets outside our integral, our interval. So what remains in the interval from the shift to the right, so from Sn of F minus Fr will be only this left triangle. So we will have this one. I'll pick again the colors. So this first one will be coming comes from Sn of f minus fr. And its friend, this one is lost because it went outside the spectrum. And then second term, Sn of f plus fr, means that we take the spectrum, we shift it to the left. So this one gets shifted to all these negative large frequencies, so they are not inside our interval minus fr to fr, so it gets deleted. And this right triangle shifts to around 0, so the middle point fc will be mapped to 0. So I'll pick another color for this. So the second one will be shifted to around 0. Let's also write down the names of the frequencies. So the middle frequency is 0, so this is minus b, this is plus b, and since these are exact replicas of the original spectrum, so they have the peak value is equal to a. So as Ni of f, the low pass in-phase spectrum, is the sum of these two shapes. So let's also draw it here as an additional figure. So Sni of f, which is also equal to Sn q of f, is the sum. We should just sum up these two triangles. So here the peak value is a, the other one is 0, so we start at a. But then this is linearly decreasing and this is linearly increasing. So loss in the blue one will be compensated by the increase in the red one, so it's going to stay constant. And then again at the end point we will have a. So it has in fact this ideal low pass spectrum. These two random processes Ni of t and Q of t. Okay. So next we could also, it's not in the question, but we could maybe also look at the joint. I don't know, I keep saying joint here today. The cross power spectral density. So let's also look at J, S, and I, and Q of f. We remember that we are expecting something low pass. So again, I'll go with the partial definition. So remember, it was nothing but, it was just like this, but then the second one got a minus sign instead of the plus sign, right? So let's write it down. So Sn of f plus f, f minus fr, then minus Sn of f plus fr. This is if f is between minus fr and fr, and then 0 outside this interval. Okay, so then we know what we have to do. We should just take again our two shapes. So Sn of f minus fr. I'll also write here for completeness. This red one comes from Sn of f plus fr, right? I don't write Sn of f plus fr exactly because it also has another part which disappears, so this is why I like writing comes from. Alright, so what we do here is simply we'll take the blue curve and then we'll subtract the red curve from it. So it's easy to do, so let's take the blue one. And let's take minus the red one. And let's complete our picture. So this is f, this is minus b, this is b, the value here is a, and the value here is minus a. So doing this subtraction, you get, so it's more convenient to write this as j times the spectrum, because otherwise you would be drawing something complex, which is also possible to do if you can represent it somehow. All right, so the blue curve minus the red curve. So here you have the peak at A, starts at A, and then so this decreases linearly. This also decreases linearly. Well, in fact, you're adding them up here. You're not subtracting. We already put the minus on. You're adding these two up. So it should be something that's monotonically decreasing, right? Because both blue one and the red one are decreased. So in the middle point at f equals 0 should add, I guess, a over 2 and minus a over 2. So it passes through 0. And at this end point, it should pass through minus a. So this is something that's linearly decreasing all the way from minus b to b. So you get this nice and clean cross spectrum. Okay. Just something to notice here. Remember this remark when we were discussing the orthogonality and uncorrelatedness of the in-phase and the quadrature processes. We said that the cross-power spectrum vanishes for all f if the PSD is symmetrical around 0, from which this is equal to 0, from which it follows that Ni and T and Q of T are orthogonal and uncorrelated random processes. Here, we don't observe it. Look at the cross-power spectrum we obtained in this example. It doesn't vanish, right? You have some non-zero cross-power spectrum. And why is that so again? It's because the symmetry assumption is not met here. So the first assumption that the representation frequency is chosen as Fc is met. This is what we indeed this. But the PSD is not symmetrical around Fc in our example. Why? Again, remember, Fc is in here. We have this, just focusing on this shade, it's not symmetric around Fc. So this is why the cross spectral density did not vanish. And we wouldn't be able to say that the random processes Ni and Nq are orthogonal here. The random variables NIT and NQT, for any t, they're still orthogonal and uncorrelated. But the random processes NIT and NQT are not uncorrelated in this example. Okay, there's a second part. So what I propose you did was is just in the second part, the lowest frequency of the bandpass is chosen as Fr. So the middle frequency is Fr. So this is what we Fc. This is what we chose as Fr in this example we solved together. And in the second one, you're going to choose Fr here, this endpoint Fc minus b. So just do that, repeat the same steps, and then obtain your shapes. The answer is given here, which I skipped quickly, so you can work on it and then compare with the answer in here. Okay, so as the final part of today's lecture, we will look at what happens to all of these random processes if the initial bandpass noise process N of t is taken as a Gaussian process. So before we go into the details of that, you might maybe ask yourself the following question. So in what kind of situations will you obtain a bandpass noise process that is Gaussian? That's a Gaussian process. So obviously, to get one very common answer to that, you can go back to this initial picture. Remember that our bandpass noise process is assumed to be obtained by bandpass filtering this white noise, initial white noise random process. So in engineering, whenever we study some additive noise component in a time varying signal, maybe like 90% of the time we assume it to be a white noise model, and if we have to assume some distribution, very, very often we assume it to be Gaussian. So this is why a white noise Gaussian process is a very commonly used noise model. So in case you have a white noise process that's Gaussian in the input of this system that's in the very beginning of this chapter, which we looked at, so then the bandpass noise process N of t will also be Gaussian. Why? We have seen this before. You pass a Gaussian process through an LTI system, the output process is also Gaussian. So this is one very common setting that you might run into when you study noise acting on a time-varying signal in engineering. So, okay. So So when we have a bandpass noise process which is Gaussian, then let's start thinking about it. All of the properties that we saw about the components, for instance, the random variables NIT and NQ are orthogonal random variables. They are also uncorrelated because they are zero mean. So if you also add the Gaussian assumption on top of this, you can also get not only uncorrelatedness but also independence, because under the Gaussian assumption, uncorrelatedness implies independence. This is one classical result we already studied before. And similarly, if you assume the power spectral density to be symmetric around the center frequency Fc, then the cross power spectral density of Ni and Nq will vanish. And then these random processes, we have seen that they're uncorrelated. But if they're also Gaussian, uncorrelatedness plus Gaussian assumption, you can get that these random processes are independent. So assuming the bandpass noise process to be Gaussian simplifies the whole picture quite further. So we'll go through all of these things in detail. So here's, before we go into the Gaussian process, a brief summary of all of the things we have seen here. So I'll just quickly go through them. So remember that the original process, if we take its Hilbert transform, we get n hat. This was White-Sand stationary, so also n hat also is White-Sand stationary. This is zero mean, this is zero mean. Then we derived all these processes, so n hat is the Hilbert transform. Take n plus j n hat, you get the pre-envelope. This is also White-Sand stationary, this is also zero mean. Then take the pre-envelope, multiply this complex exponential, you get the complex envelope or the low-pass equivalent random process. You can then get Ni and Nt in terms of the original bandpass process N and its Hilbert transform. Then here's a nice table that gives you a summary of all the things that we have seen so far, all these processes N hat, and then the cross correlation functions between them, and the pre-envelope, low-pass equivalent, the in-phase components, quadrature components, their autocorrelation functions, and what they correspond to in the frequency domain. So we have seen each one of these. I think I let you go through this table carefully so that you can make sure you don't miss anything. Okay, so now let's skip to the discussion in particular for Gaussian processes. All right. So what we will try to do in the rest of this today's lecture is we will study the statistical properties of all of these signals. What is the distribution of Ni, what is the distribution of Nq, and all of these things, if I assume that the initial original bandpass noise process is Gaussian. Okay, so let's go step by step. So first of all, N of t is a Gaussian process. So let's maybe begin with the following picture. So it all begins with the Hilbert transform process, right? So in this definition, well, if we just follow this flow, we took n, we defined n hat, so from these two we defined the pre-envelope and so on. So let's maybe kind of follow this order. So let's begin with the properties of n hat. So what we know is that n hat is obtained from n of t by passing it, actually taking its Hilbert transform, so by passing the Hilbert transformer LTI system. So this enters, and at the output we get the Hilbert transform process n hat of t. So we know that this thing is White-Sand stationary. We assumed it to be ergodic, which also implies that it's White-Sand stationary. So White-Sand stationary input entering an LTI system. By the way, we will be skipping the rigorous treatment. Well, this is not stable. So we show that if a White-Sand stationary process enters a stable system, the output is White-Sand stationary. But we'll kind of relax that stability requirement here. So for this course, for almost any example you might encounter in this course, you might comfortably assume that if you have a White-Sand stationary process going through an LTI system, you might assume that the output is White-Sand stationary for practical purposes. So we won't go into pathological examples where things go to infinity and the WSS assumption is not met and so on. So white sun stationary entering an LTI system, the output is also white sun stationary. We showed that this is. Now what we are doing right now is that what is new here is we will also assume it to be Gaussian. Okay, so N of T is Gaussian. It's a Gaussian process. Now, if we assume this to be a Gaussian process entering an LTI system, let's just say LTI here, Gaussian process entering an LTI system, the output process is also Gaussian. So this is why in this first item, the Hilbert transform is also a Gaussian process. And moreover, we also proved the second item when we were studying Gaussian processes. So if a Gaussian process enters an LTI system, the input Gaussian process and the output Gaussian process are also jointly Gaussian. So let's also note it here. They are jointly Gaussian. And head of T and N of T. Now what's more, here, so the input process is a Gaussian process, which we assumed right now, and it was also a white sun stationary process. This was one of our previous assumptions. So if a Gaussian process, well, remember, in general, a white sun stationary process does not have to be stationary in the strict sense, but we showed that if we assume the process to be Gaussian, then the white sun stationarity assumption implies strict sense stationarity. So white sun stationary plus Gaussian, it just implies that the input process is strict sense stationary. But you can do the same thing for the output process. The white sun stationary process, we just saw that it's Gaussian. These two imply that the output process, the Hilbert transform process, is also stationary in the strict sense. So this is the third item that we have seen here. Now, for the moment, we won't immediately go into the processes NLP and N plus. What we will do instead is we will focus on the in-phase and the quadrature components of NLP. One reason is the following. So for the moment, we are studying real valued processes right now. So N is a real valued process. N hat is also a real valued, the Hilbert transform. N plus is a complex valued process. So let's just skip it for the moment. NLP is also a complex valued process. Why? It has an NI part, so plus, and Q part, so it's complex valued. Let's just immediately skip to what NI and NQ are, because these are real valued processes, right? So here, the NI component and the NQ component, these are real values. So let's look at what they are. So now, when you're dealing with Gaussian processes, probably the first thing that you might want to check is whether the resulting processes are Gaussian or not. So what this property now tells us is, here I think we're in the fourth one. So Ni and Nq are obtained from jointly Gaussian random signals and N hat by linear operations. So let's look at that. Let's confirm this. So Ni is obtained by taking N and then N hat, and you're multiplying them with some certain values, and NQ is obtained similarly. So first of all, let me ask you, let's simplify it. Before we go into whether Ni of T is a Gaussian process, let me ask you the following question. Fix any T0, so evaluate Ni of T at T0. So let's look at the random variable Ni of T0 for some T0. Is that random variable a Gaussian random variable? Let's first think about that. So we just need to look at this equation. So I evaluate things at T0. So N of T0, what is that random variable? What kind of random variable is that? It's a Gaussian random variable because this process, we just assumed it to be a Gaussian process. Now similarly, n hat, we have just seen that it's a Gaussian process, so if I look at it at t0, I get a Gaussian random variable. The Gaussian random variable plus times some coefficient just by evaluating the cosine at t0, I just get some real number, plus n hat of t times another coefficient. So I take the linear combination of two Gaussian random variables. So the resulting random variable is also going to be Gaussian. In fact, more precisely, here you're taking the linear combination of two jointly Gaussian random variables, because the processes n and n hat are just seen to be jointly Gaussian. So take two jointly Gaussian random variables, take a linear combination, the output random variable is a Gaussian random variable. So similarly for here, nq of t at any t0 is going to be a Gaussian random variable. So, but what we're trying to argue here is that these are not only jointly Gaussian random variables at some certain t0, but we would like to show that they are also jointly Gaussian random processes. So remember, to show that two random processes are jointly Gaussian, what you need to show is that take several samples from the first random process. Let's say take ni of t1, t2, t3 up to some tk. And then also take samples from nq at some arbitrary, possibly other time samples. Let's say t1 prime, t2 prime up to some tm prime. You should show that all these random variables considered together, they are jointly Gaussian. So to show that in a rigorous manner, I mean, I'll skip the rigorous proofs here, but I'll just give you the idea so that you can work on them if you want. You can just take a piece of paper and do the following. Look at this first equation, evaluated at some t1 and then some t2, t3, up to some tm of your choice. And then look at all these random variables. Then do the same thing for this guy. Look at some t1 prime, t2 prime, etc. up to some tm prime. And then you have a couple of random variables. Now, fixing these time instances t1, t2, and so on, these cosines and sines shouldn't be confusing you anymore. They just become some coefficients. They are just some coefficients changing between -1 and 1 for each t1, t2, and so on time instant values. So what's happening is the random variables that you're forming in this way from ni and nq, they are all obtained by taking linear combinations of these jointly Gaussian random variables. So the first one comes from the samples of n of t, and the other one comes from the samples of n hat. So you take linear combinations of jointly Gaussian random variables. At the end, you get jointly Gaussian random variables. So this is the basic rule about the joint Gaussian density. So you can repeat this for any choice of t1, t2, and t1 prime, t2 prime, etc. values. You'll always get jointly Gaussian random variables, which is nothing but the definition of jointly Gaussian processes. So these are jointly Gaussian processes, which all comes from the fact that n and n hat are not only Gaussian random processes, but they are jointly Gaussian random processes. So if these are getting you confused, you can just go back to the notes of chapter, I don't remember, but the chapter on Gaussian processes. Oh, okay. Now, all right, Ni and Nq are jointly Gaussian processes. Now, another property here. So what do we know about Ni and Nq? We showed already before that these are Weissan stationary. Now we just argued that they are jointly Gaussian. So each one of these, so Ni of t, it's Gaussian, it's Weissan stationary, which implies it's strict sense stationary. The same thing for Nq. So then up to now we know that these are Gaussian, these are Weissan stationary, these are strict sense stationary. So let's look at what these things imply also about the uncorrelatedness and independence things. Now, first of all, let's look at these as random variables. So remember, fix any time instant t. So take this random variable nit and take nqt. So remember here at some point we studied what their correlation situation is, so I guess it's here. Okay, NIQ and NQT, we first show that they're orthogonal because multiply them, the expectation is 0. But then these are also zero mean, which implies that these are all uncorrelated. Now, we are also assuming that these are Gaussian. So uncorrelated random variables, which are Gaussian, it implies independence. So Ni of t and Nq of t, take any t value, these two random variables are independent random variables. So this is what the sixth property tells us. Now, in the general sense, you can't conclude that Ni of t and Nq of t are independent random processes. You can't say it in general unless you make a certain assumption, and the assumption is that the bandpass process N of t has a power spectral density that's symmetric around the center frequency Fc. So remember this, we looked at this. So if the blue one came from the left part and the red one came from the right part, and if this is symmetric, it means the left part is exactly the same as the right part of this hill-shaped thing, which just comes from one wing of the spectrum. If these are symmetric, so these two will cancel, so the cross spectrum is going to be 0, which means that the cross correlation function is going to be 0, and then this means that Ni of t plus tau and Nq of t are orthogonal random variables. So I guess we could just add this as this line. So this autocorrelation function is nothing but Ni of t plus tau and times Nq of t. I'm just skipping the complex conjugate sign because these are real. So these two random variables at any t and t plus tau are orthogonal, but the whole random process is zero mean, so these two random variables are uncorrelated. But then you have two random variables that are uncorrelated. We know that these random variables are also Gaussian because we assume that these processes are Gaussian processes, which from which we get that these two random processes are independent random processes, which is here. But again, to be able to do that, we have to we need the assumption that the PST is symmetrical around the center frequency Fc. All right. So this is these are the basic principles about how to extend our previous properties to the case of Gaussian random variables. The idea is that, just a summary, N is Gaussian, N hat is Gaussian. These are the real valued processes that are in our picture. And I and NQ are also real valued. They're also Gaussian. They're jointly Gaussian. And then under the Gaussian assumptions, uncorrelatedness implies independence. So these are the only tools that we have used. Okay. Now we're asking the following questions. What about the probability density functions of these random variables? So if I take a sample, let's now think about taking samples. I take a sample from my Gaussian process, I get a Gaussian density. I know that this is the definition of the Gaussian process, right? So N of t is a Gaussian random variable. Now Ni and Nq, if I take samples from these, what kind of density am I going to get? Well, we just showed that these are Gaussian, but so these have the Gaussian density, but let's look at this in more detail. So let's go step by step. So that I just put some blanks here so that you can fill in, just to remember what we have seen. So the bandpass noise is the Gaussian process. So we just saw a moment ago that Ni and Nq are what they are jointly Gaussian. So N of t is a Gaussian process. This implies that Ni of t and Nq of t are jointly Gaussian. Again, this came from the argument that these are obtained by taking linear combinations of some jointly Gaussian random variables. So in the second place, well, if these are jointly Gaussian random processes, if I take Ni of t at some certain t value and q of t, then I should be able to write down their density, the individual PDFs, right? They are just the Gaussian density. So let's just write it. So let's try to write down the density for Ni of t. Here again, this is a random variable. Now we have fixed t. We're writing down a density expression. So a density is a function of x. Don't get confused. So this density is the same as the density of NQ of t. And they are both equal to, well, we should just write down the expression for the jointly, for the Gaussian density. So 1 over 2 pi sigma squared and e to the minus. So here, you know the Gaussian density expression, you would write x minus mu squared. But what is mu again? Mu is the mean of this density, right? But what is the mean of this? What is the expected value of this random variable? It is 0, so we could skip mu. So mu is 0. So we can just simply write e to the minus x squared. And here we would write the variance expression, so 2 sigma squared. So now this is the variance of your Gaussian density. You don't know what that variance is. It depends on the process you have. But here, sigma squared is the variance of this density. But this random variable is 0 mean, so it's equal to the mean square of this random variable. So this is equal to the mean square of Ni of t, and also similarly equal to the mean square of NQ of t, and so on. So, but then these are ergodic processes, so their mean square is equal to their average power. So in fact, you could see this variance expression here as the average power of these random processes in some way. So here is a reminder for you. Okay, now if you move on, these processes are wide sense stationary and they are Gaussian. So we just saw that these two imply together strict sense stationary. So Ni and NQ are stationary in the strict sense. So let's write it. So Ni of t and Q of t, these are Gaussian plus wide sense stationary, which implies that they are strict sense stationary. But then if you're interested in the implications of this only regarding the first order densities, if a process is stationary in the strict sense, that means that it's for sure first order stationary, right? So the implication would go on. SSS implies first order stationary, which totally makes sense because we just wrote here the first order density of these processes, and nothing here depends on t, on the time instant that we're looking at. So for any t, this random variable always has this density which has no dependence on t. So this is coherent with the implication that Gaussian plus wide sense stationary gives you a first order stationary process. Okay, so the first order PDF expressions were given here. Now, well, if they're Gaussian, we saw that these two random variables, which are normally uncorrelated, become also independent. But then if they are independent, we can completely write down their joint density because it's as easy as multiplying together the first order densities that we wrote down in here. So to get the margin, to get the joint density, take Fni, take the density of NIT, which is here, and then the density of NQ of t, which is here. So you multiply them, you know the joint density. All right. So after this point on, what we have done so far is we know the density of N of t, we know the density of Oh, n hat of t, we know the density of ni and nq. These are all Gaussian random variables. But can we take this any further? What about the, let's go back to our initial drawing in here. Just jumping too much. Wait. I'm sorry. I'll just use the scroll bar. Here. So what about the density of n plus and nlp? Let's maybe focus on nlp because we have already explored its real and imaginary parts. So ni is Gaussian and q is Gaussian. Fix any t. Let's say that we're looking at it at a single t moment. These are independent Gaussian random variables. Now, what about this one? Now, first of all, this is a complex valued random variable, nlp of t. In our discussion of the Gaussian density, we restricted to real random variables, and we didn't define anything like Gaussian density for complex random variables. So, nlp of t, all right, I mean, we won't call it Gaussian. However, it doesn't have any chance to be Gaussian because it's complex in our setting. But then you might say, okay, but then maybe if I look at, well, this is complex, but what happens if I look at its magnitude? So let me take the magnitude of this random process. So I get R of t, and then it has a phase part, so nlp can be written in this way. Now, what about R of t? Could I expect it to be a Gaussian random variable, or if it's not Gaussian, what kind of density does this have? When you are looking at such questions, actually, when you are analyzing some entity in an engineering system, very often you start with a Gaussian assumption for some entity, which is reasonable, like something additive, something noise, something related to many different factors. From the CLT, it's usually a very good assumption to think that it's Gaussian. And then you have some other entities that are related to the original one. Then you're wondering, I assume that this first one was Gaussian. Can I also claim that the other ones are Gaussian? This is some typical situation that you might encounter from time to time. Now, remember, when we looked at Ni and Nq, how did we conclude that they are Gaussian? Make it easy, just fix a single time instant t. Let's say we look at these equations at some t or t0. Gaussian random variables, n and n hat, these are jointly Gaussian. Taking linear combination, it produces Gaussian. So actually, by the time that you have acquired some experience, some reasonable amount of experience with these things, there's a Gaussian flag in your brain. Whenever you see that two Gaussian things are taken and combined through a linear combination, then the Gaussian flag in your brain gets odd. So linearity just turns on the Gaussian flag. Can we say something similar for R of t? I mean, is this something that has a linear flavor or not? Now think about what it is. It has a real part and an imaginary part. So it's the magnitude. So what you're doing to obtain R of t is basically you're taking Ni of t, taking the second power, then taking the second power of Nq. You're summing up the second powers, then you're taking the square root. This is the definition of the magnitude of a complex number. So the actions that you're taking are very nonlinear, right? Taking squares, summing up, and then taking the square root. So the linear flag is not on. So you can already maybe say that, okay, this thing shouldn't be Gaussian. Well, a very brief argument to tell you immediately that it's not Gaussian. What is the range of this random variable R of t? It's radius, right? It's magnitude, so it can't be negative. It has to be non-negative, so it can't be Gaussian anyway. A Gaussian random variable should cover the whole real line. So this is not a Gaussian random variable. Then we ask, what is it if it's not Gaussian? So this is what we are going to study right now. All right, so this is the real part of the low-pass equivalent process. So we might, in fact, extend the question: what is the density of the envelope process R of t, and also the phase process theta of t? Now, the argument will be through the densities of Ni and Nq. So first of all, let's begin with a picture here, which you might draw here. So let's geometrically visualize our low-pass equivalent random process NLP of T. So let's visualize it in the complex plane. So it has a real part, and it has an imaginary part. So we can visualize it as a vector. So let's draw some vector. This is the NLPT. Its real part here is going to be equal to Ni of T, and its imaginary part is going to be equal to Nq of T. So I'll just indicate this on my figure. So the real part is going to be Ni of T, and the imaginary part here is going to be Nq of T. Well, then this is our process NLP of T. So it's a bit, I find it funny to try to visualize these things. So yeah, what you're imagining is you have a random process. Well, it's a random vector. This is a random vector. Its real part has a Gaussian distribution, zero mean Gaussian distribution. Basically, this x component could be anywhere on the real line. Its mean is 0. It could be here. It could be here. It could be large. It could be small. Similarly for Nq of T. And for each T value, you're taking this real component, combining it with the imaginary component, and that's giving you a vector. So you have here a vector that's just wandering around here and there on the complex plane. So then what we are, in fact, this could be error. It could be in the first quadrant, second quadrant, because this Ni and Nq could be a real, it could be any real number. Now, what we are interested in doing is we will try to study the density of this, which will be the same as studying the joint density of Ni and Nq. Because this thing, being complex, is inherently two-dimensional in some way. Now, what we will be studying is the probability that this is within some certain region, a small region. So let's just take a square here. Some certain zone in the complex plane. So let's just mark its endpoints. So let's call this one x. So this point will be x plus dx. You see where I'm going with that. This dx is going to be infinitesimal, and we will write down probability expressions in terms of the joint densities and so on. So this point is y. This is y plus dy. Okay. And then we will be interested in the probability that our random vector NLP of T is within this certain region. Now, we can write down the same thing. We can actually generate the same picture, but in another coordinate system. So if you use Cartesian coordinates, x and y, this is what you get. So the components are Ni and Nq. But then if you express this random variable at a fixed time instant t, in terms of the polar coordinates, then you get the r and theta components. So I'll just draw the same figure, but this time in another coordinate system. So this is the same NLP of t vector. So now this time r of t is going to be the magnitude of this, right? So this is going to be r of t random process with the tilde here. This is just supposed to be an r. Sorry for my awful writing today. R of t. Okay. And the phase of this is going to be theta of t, phase random process. These are nothing but the random processes. These random processes, right? The magnitude part and the phase part. Now, changing our coordinate system, and we will write this in the r theta representation. So let's say that this square more or less corresponds to this region in the r theta domain. So this is some certain r value. Just imagine some arc here, some circle segment, so r, and then this one would be r plus dr, as if like dr was the width of this region. And then this theta value is, this shouldn't be curved by the way. This theta value, let's call it as theta, and then the end theta value would be theta plus d theta. So let's say that this region was chosen such that this square in the xy plane more or less corresponds to this region in the r theta domain. Now obviously they don't have the same shape, but when you take this analysis to an infinitesimal level, you can just simply approximate this area as this one. So this is going to be the idea. Now, of course, the change of variables that gets you from xy to r theta is, from the calculus classes, we know that this x is equal to r cosine theta and y is equal to r sine theta. X and y could be anything from minus infinity to plus infinity, but there are restrictions on r and theta, so r can't be negative, it's non-negative. And by convention, we put also some limits on theta. So you could pick 0 to 2 pi or minus pi to pi, doesn't matter. Let's go with minus pi to pi. So theta varies in this range and r varies in this interval. Okay, so now the argument will be the following. So since this region is more or less the same as this region, if x, y, and r theta confirm, they obey these relations, then the probability that my random variable NLP, my random vector NLPT is somewhere within this rectangle is the same as the probability that it's somewhere within this region. So writing this first probability, so and LP of t being within this rectangle would be expressed as this. This real part should be between x and x plus dx, similar for the imaginary part. So it's the same expression. This is equal to the probability that n LP of t is within this region in the r theta domain, which is written in here. Now the trick will be to take these probability expressions and then express them in terms of the joint PDFs. So we know that when dx and dy are sufficiently small, this can be approximated as the joint density times dx dy. And then doing the same thing for here, this should be the same as the joint density of r theta times dr d theta. So this equality holds. Now, what we will do next is we will consider the transition from these two sets of variables. So when you pass from xy to the r theta system, remember from our calculus classes, there's a Jacobian that you have to take into account. So dx dy is equal to r dr d theta. So doing this change of variables, let's maybe write down the equations we have. So let's begin with the joint density of Ni and Q. So F Ni of t and Q of t, xy, dx dy. I'm just starting with this expression, right? I'm just developing it. So let's write down in terms of its analytical formulation. So remember the joint density we already derived in the previous section. So this is the joint density we have. So let's write this down. So this is 1 over 2 pi sigma squared, because two roots get multiplied. And then e to the minus, well, this x squared term gets summed up with the y squared term. So e to the minus x squared plus, I think I'm hitting, okay, I made it, divided by 2 sigma squared, and then the dx dy term. Okay, now let's make the change of variables. So let's switch from the xy representation to the r theta representation. So we should rewrite all these terms in terms of x and y, this time in terms of r and theta. So this is a constant, it remains the same, 2 pi sigma squared, and then e to the minus. So what is x squared plus y squared? Again, through this change of variables, x squared plus y squared is from the triangular argument. This is nothing but r squared, right? So in the numerator, I have r squared. Then the variance is the same, 2 sigma squared. And then when you're switching from dx dy to dr d theta, the Jacobian of that change of variables is, you can go back to your calculus notes if you're uncomfortable, but then the Jacobian comes out to be r. So you have r dr d theta. But now going back to the origins of this equality, we start with this one, which came from the probability, equality of the probabilities. Now the whole expression that we developed for this one needs to be the same as f r theta dr d theta. So we can now equate this to f r of t theta of t r theta dr d theta. Don't get confused here. T is something fixed throughout all these derivations. T is just a time instant. I know where my arrow is, so I'm just looking at the corresponding random variables. Okay, T is fixed. So okay, but then now comparing these last two equalities, so dr d theta factors are the same. So the expression which you see in here, which is the joint density of r of t theta of t, has to be equal to this one, including r. Now, from this, we have finally obtained the joint density of r of t theta of t. Now, remember, our initial purpose was to look at what the density of the random variable r of t was. So we suspected whether it was Gaussian, then we concluded it cannot be Gaussian, then we're right now trying to find out what kind of density is it if it's not Gaussian, right? So the joint density is here. Now, of course, we should we should pay attention to the interval. So theta is within this interval, and r can't be negative. Otherwise, we should take the density as 0. Now from this, we can finally find out what the distribution of r of t should be. It just all we need to do is to marginalize the distribution. Remember, if you integrate the joint density over theta, you'll get the marginal density of r. So doing this, you get this expression y. In fact, imagine that you're integrating this expression over the range of theta values. So you're integrating between minus pi to pi to do the marginalization. But nothing in this expression depends on theta, right? So basically, the integral would be the same as taking this and then multiplying it with 2 pi, which is the interval from minus pi to pi. So basically canceling this 2 pi factor. So what you get is r over sigma square and the rest of the terms under the extra condition that r can't be negative, so u of r. So this is the distribution of r. And what is this distribution? So it is not Gaussian. It has this term here, but it can't be negative, and there is this extra r term that gets that multiplies this Gaussian looking like term. So if you draw this, let's try to draw this density. So let's draw the density of r. So f r of t of r. So it can't be negative, so it's all 0 all over here. And then as r starts increasing from 0 on, this linear term will make your function value increase. So there's some linear increase, almost linear increase. And then you start seeing the effect of this exponential decay term. So at large r values, this second term, the exponential term will take over, and then it will decay to 0 at larger r values. So this is the distribution of r. So this is called the Rayleigh distribution. My computer is not responding again. Okay, so it's interesting to know if now, tomorrow, somebody comes to you from, I don't know, a civil engineering department, some friend or someone, they tell you, oh, I have this complex vector. I know that each component is Gaussian, and I'm interested in the magnitude of this vector. And these are independent Gaussian random variables, by the way. But what is the distribution of this vector? If you encounter such a situation, now you know that it's not Gaussian, it's the Rayleigh distribution. Which has this density. Now, going back to this marginal density, now if you have, you can do the same thing to obtain the density of theta. So now if you marginalize this over R, means that you're integrating this for positive R values, and you're killing R out, that you get the dependence on theta, you will get this density. But there's an easy way of seeing it. So inspecting this joint density, we observe that it has no dependence on theta as long as theta is in this interval. It's constant with respect to theta. So obviously, if you take this theta or another theta, it will be exactly the same because nothing in it depends on theta. So this is why we can immediately see that this density, the density of theta should be uniform. So you can confirm by marginalization integrating over R. So theta is uniformly distributed within the region minus pi to pi. So you could also plot the density of the phase term. So minus pi to pi, it has this uniform density. And the value is, of course, 1 over 2 pi. That's interesting to think about this. Going back to this initial picture, the x component is 0 mean. The y component is also 0 mean. But the magnitude is, of course, it can't be 0 mean because it has to be positive. So the shape for R is something like this. It makes a peak at some non-zero R value. Of course, this value depends on what sigma is. And then when you think about the phase, like the direction of this vector, and the components Ni and Nq could be anywhere. Their independence is completely symmetric. So there's no bias in some way on the phase of this or on the direction of this vector. So any direction is equally probable, equally likely, let's say. So this is why it is quite reasonable to obtain a uniform density for the phase term or the direction of the arrow in some way. All right. So this is about the R of t and theta of t random variables. So I guess this is the end of the class. So there's just a small remark here about the, I think some of you might be confused with this. Well, when we were studying LTI systems, we always started with the stability assumption. We say that let's assume our LTI system is stable. Then if I have a White-Sun stationary input, I get a White-Sun stationary output and similar other properties. But in practice, well, in many of the typical exercises we solve, for instance, we use a lot ideal low-pass or band-pass filters, but these are not stable systems. This remark is just to kind of relieve you or relax you and say that, I mean, don't worry if they are not stable in many cases. Even if the system is not stable, if it has some nice properties like h of 0 being finite or the Fourier transform not exploding, you'll get something reasonable. So White-Sun stationary input will imply White-Sun stationary output and so on. So you could just read this remark carefully. And similar expressions hold for the relation between Sx and Sy. So I guess that's it. So this is the end of our class. So I would like to thank all of you. So if you are watching this video at this point right now, it means that you have made it until the end of this these tough times. It was tough for everybody. It was hard for us. It was, I guess, even harder for you. But we made it. We are warriors. So I think that you will have your final exams also online. So we won't be seeing each other until September. So I wish the best of luck for everybody in your final exams, and I hope that you will have a wonderful summer with your loved ones. And I hope to see you everybody back in September. So bye.